My name is Mike Wooldridge. I'm a professor of computer science at the University of Oxford in the United Kingdom, and I've been an AI researcher for 30 years. What I want to do today is to talk about one aspect of artificial intelligence, which I think has been overlooked in the last few years as we've seen so much excitement around machine learning in general and deep learning in particular. And that is to do with the idea that the future of artificial intelligence will not be isolated systems that sit on their own and do not talk to other systems. And it won't be systems which just talk to human beings. It will be AI systems which interact with other AI systems. So this is an old idea, but what I want to do in this talk is to explain to you why I think this is an important idea, where this idea came from, and crucially, what we need to do in order to make this a reality. So, if we go back to the history of computing, go back all the way to the late 1940s and early 1950s, we can identify immediately some trends which have been ongoing throughout the history of computing since then. And I want to talk a little bit about these trends because they're important to understand what the future of AI is going to look like. So the first trend is towards ubiquity. So when we say something's ubiquitous, we just mean it's everywhere. Okay, so something which is ubiquitous is just everywhere. And in computing, when we talk about ubiquitous computing, what we're talking about is the idea that computer processes become embedded everywhere. In every artifact that we construct, in every device that we build, we can imagine placing computer processing power and decision-making capability, information processing capability, intelligence of a kind. So where the ubiquity trend comes from is the famous Moore's law. So there are many different versions of Moore's law, but basically what Moore's law tells us is that computer processors get smaller and cheaper and require less power every year. And this trend has held good throughout the last 60 years or so. So Moore's law tells us that we can put computer processors into places and into devices that we couldn't have imagined previously. And that's going to continue. So the future of computing is going to continue to be computer processors embedded everywhere. The second trend is towards interconnection. So when I talk about interconnection, I just mean that these devices communicate with one another. So when I was an undergraduate student, and I was studying computer science, I took a course on networks, and the lecturer said, well, you know, these are difficult things to build, but don't worry because you probably won't encounter one out in the wild. Well, that lecturer was completely wrong. We now understand that networked, interconnected computer systems are the norm in computing, and we will have ever more interconnection in the future. So the first trend towards ubiquitous computer processors everywhere, and the second trend towards interconnection, these computer processors communicating with one another. The third trend is towards delegation. And by delegation, I just mean that we hand over control of more and more of our lives to computers every year. So an extreme example of this, again, going back to the 1980s, was when companies like Airbus started to roll out fly-by-wire aircraft. And in a fly-by-wire aircraft, a human was out of the control loop. Ultimately, there was a computer program that was doing the control of the aircraft. And today, of course, we're on the edge of seeing commercially viable driverless car technology, which will roll out at some point over the next few years. And these are extreme examples of delegation where we're handing over control, we're handing over decision-making for us to computers. The next trend is towards human orientation. And all this means is that the way that we interact with computers gets ever more like the way that we interact with people. And the most obvious manifestation of this trend is towards natural language interfaces. When you talk to your Siri or your Alexa or Cortana, you do that by issuing instructions in English or Russian or Mandarin or whatever. It's a human-like interaction. And these interfaces are still quite primitive, but they're going to get better and better over time. And then the final trend, and the reason that we're here today, is the trend towards intelligence. And this is nothing like as dramatic a trend as Moore's law, despite what the popular press would have us believe. But basically, computers are getting smarter. Okay, they're getting smarter year on year, and that will continue. So these 5 trends have been ongoing throughout the history of computing, but I think it's a safe bet that they will continue to be ongoing for the foreseeable future. So I don't know exactly what the future of computing will look like, but it is for sure going to be ever more ubiquity, ever more interconnection, ever more delegation, ever more human orientation, and ever more intelligence. So that's what the future of computing will look like. And we can see many different manifestations of that future, many different developments in computing that hint towards that future. So cloud computing, the idea that your compute resources are not on your desktop, but that you're connected to them via a network and they're accessible to you wherever you are in the world via a network. Okay, that's emphasizing the ubiquity, emphasizing the interconnection. Similarly, the idea of peer-to-peer computing, the idea of ubiquitous computing, the idea that our environment is populated by computer processors which are sensing us, watching us, and assisting us as we carry about our tasks in the real world. The idea of the semantic web, the idea of enriching the World Wide Web with intelligence. That's what the semantic web is basically all about, is emphasizing the interconnection and the intelligence. The grid, the idea of availability of compute resources, virtualized compute resources on a very, very large scale. So you don't even worry about where those compute resources are. Again, emphasizing ubiquity and interconnection. But if we turn to artificial intelligence, where do those trends take us? Where do those 5 trends take us? Well, what I'm going to argue is where they take us is to what we call multi-agent systems. So the dream of intelligent agents is now quite an old one. I started work on AI in the late 1980s, and this idea of intelligent agents was just beginning to be formulated at that time. And the idea is that you have software which works as an active assistant with you, working on a problem. So in the same way that you would have a human assistant who is helping you in, say, your office tasks, a human personal assistant who's helping you in your office tasks, the idea of an intelligent agent is you have a piece of software which is actively working with you. It's not waiting to be told what to do, right? Most applications that we use on computers today, Microsoft Word and PowerPoint and whatever, basically they are the dumb recipients of our instructions. They are waiting for us to tell them what to do. They never take the initiative. The idea of intelligent agents is that rather than just waiting to be told what to do, the software is an active collaborator with you, and it acts semi-autonomously on your behalf. Okay, so it's software which is acting for you. Remember, I talked about delegation. You can see the idea of delegation reflected there. So it's not a new idea, as I say. We started working on this idea in the late 1980s. What's made it feasible now, why it's a current idea, is the availability of smartphones. We all carry a smartphone with us. Basically, a smartphone is a supercomputer that we carry in our pocket. The availability of big data, with which we can empower these agents. The use of new AI technologies like deep learning, which have made natural language interfaces viable in the last few years, and so on. So there's a confluence of different technologies which have come together in the last decade or so that's made the dream of intelligent agents a viable reality now. But at the core of all of those technologies is artificial intelligence. So the dream of intelligent agents then is that we shift away from the idea of software as a passive service or a servant or assistant, a passive service, to software which is a proactive, cooperative assistant, something which is working with us. Okay, so that's the dream of intelligent agents, and we see it around us today. As I say, we all carry a smartphone with us in our pocket, and those smartphones carry with them a realization of the dream of intelligent agents. And the way it works at the moment is that, if I want to arrange a meeting with my boss, the vice chancellor, I say, Siri, arrange a meeting with the vice chancellor, and Siri says, will do, boss. And what happens is the state of the art today is that Siri would phone up my boss and say, hello, Louise, Michael would like a meeting as soon as possible. And Louise says next Tuesday at 2 p.m. works for me. And the meeting is arranged. So that's the state of the art today. And there have been demonstrations of such systems over the last 15 years, these systems that can do this kind of task on our behalf. But what I want to argue is that that realization of the dream of intelligent agents is missing an important part of the puzzle around the dream of intelligent agents. So what is the part of the puzzle that it's missing? The part of the puzzle that it's missing is that AI can talk to AI. If I need to arrange a meeting with my boss, why would Siri phone my boss? Why doesn't Siri talk directly to my boss's Siri? So in this version of intelligent agents, I say, Siri, arrange a meeting with the vice chancellor. And Siri says yes. But what it does is it talks directly to my boss's intelligent agent. So the interaction is not between a person and an agent, but between the agents themselves. So it's the agents that are doing the communication to realize the task that I've asked them to carry out. And so in this dream, they communicate with one another, and they come back to me and say, Mike, I've booked a meeting with Louise for Tuesday at 2 p.m. And Louise's Alexa says the same thing. So that's the dream of intelligent agents. And what I'm arguing is that the next step in AI is to go from having these assistants that work with us to assistants that work with other assistants. So AI agents that work with each other. So what do we need to do to be able to make this dream work? Well, the first and one of the most important things to do is that your agent needs to know what your preferences are. So what do I mean by that? Well, when I work with my personal assistant, my human personal assistant, and let's say I need to book a flight to Moscow, and I say to my assistant, please book me a flight to Moscow. For them to be able to do that simple task well, they need to know my preferences, right? So, for example, they need to know that I don't like flying via Paris, because whenever I fly via Paris, my bags get lost. I'm sorry, Charles de Gaulle Airport, but that always happens when I travel through you. So a personal assistant will know that preference and make use of that preference while they are working with me. So to go back to our meeting booking example, some simple things about meetings. So I prefer to keep all my meetings clustered, right? So to free up as many big chunks of time as I possibly can. I prefer not to meet too early in the morning. I prefer not to meet after 6 p.m. in the evening, all of these different things. Now, a good human personal assistant will make use of all of that knowledge about my preferences when they work with me. So your agent, if it's going to do things like this for you, it needs to know what your preferences are. Otherwise, it won't be able to do this task well. So how does an agent learn your preferences? Well, for example, in the meeting booking case, what it can do is it can look at your past diary, right? So a new agent that's working for you can look to see, well, when does Michael book meetings normally? He doesn't book them before 8 o'clock in the morning. He doesn't book them after 6 p.m. in the afternoon. And it can make use of that information going forward. So that's one way. It can make use of previous data about you. But more than that, and more usefully, what it can do is it can watch you. It can watch you and it can learn from you. As you handle your email and you arrange meetings, it can look to see what you're doing. Email handling agents are another classic example. Email that helps you agents that help you prioritize your email so that you can manage your large email in tray effectively are another very natural application of intelligent agent technology. So the agent can watch you as you work and can learn about your preferences via what you do. Okay, so your agent needs to know your preferences, but it needs more than this. And what else does it need? It needs to share meaning. So when we communicate with one another, we use a common vocabulary with terms that have standard accepted meanings. In exactly the same way, if agents are going to work with other agents, if software agents are going to work with other software agents, then they will also need to be able to share meaning in that way. Okay, so that's a difficult challenge. And the area which is concerned with sharing meaning in artificial intelligence is called ontologies. So ontologies are defined vocabularies of terms which agents can use. And when an agent says, I'm using this particular ontology, another agent can then know which ontology it's referring to and use the same one. So in short, when one agent says a centimeter, they both know what they're talking about, the same thing. So that's one very basic skill. They need to be able to talk the same language with the same commonly agreed terms. But they also need, what I'm arguing now, are social skills. And the social skills that they need beyond sharing meaning, which is the most fundamental one, talking a common language, is the ability to cooperate, coordinate, and negotiate. Okay, so let's talk about these. So this is a scenario called disaster robotics. It's a well-known scenario in artificial intelligence. It's being studied by many researchers. And disaster robotics, the field of disaster robotics, was prompted by a couple of natural disasters, as it happens, both in Japan. So the first was the Kobe earthquake in the mid-1990s, I believe 1996, a devastating earthquake which killed thousands of people in the city of Kobe. And in the aftermath of that earthquake, there were many buildings in the city which were damaged too much for human rescue teams to be able to go in and explore. It was just too risky to go into these partially collapsed buildings that were on fire, and so on. And many people died who otherwise wouldn't have died if we'd been able to get to them inside those buildings. They would have been able to be saved. The second disaster that prompted this work was the Fukushima nuclear power plant disaster following the tsunami in March 2011 in Japan. And what happened at Fukushima was that after these nuclear power plants were flooded by the tsunami, what the investigators and the rescue teams really wanted to be able to do was to go into these nuclear power plants and explore them to understand what damage had been caused, which systems were still functional and which were failing, and so on. But the problem in this case, it was radiation. There was just too much radiation present for the teams to be able to do that. And as a consequence, we were deeply frustrated by being unable to get access to up-to-date information about what was going on there. So what we really wanted was teams of robots, and that's the dream of disaster robotics, and that's what I'm illustrating on this slide here. So we've got a building which has been damaged. It's got a bunch of rooms in this building. There are a number of fires. And what we want to do is we want to send robots into this building to be able to explore, to find out, what's going on in this building, where the survivors are, what condition the survivors are in, and so on. So what do our robots that are going to go in there need? Well, the first thing they need, and I haven't put this on the slide, but this is a really tricky one, is they need to be dexterous enough to be able to go into these spaces. This is a big problem for robotics at the moment. By that, I just mean that the human beings are actually physically very malleable things. We can make our way into tight spaces and awkward spaces, and we can contort ourselves to get around complex environments and so on. Robots at the moment are not very good at that. Right. So there's a huge amount of work going on in order to build robots which are much more dexterous, but there's a long way to go. Right. The most dexterous robot of the present day is nothing like as dexterous as a human being. But what kinds of software skills are these robots going to need? Well, what I'm arguing is they're going to need things like the ability to share information. So as a team, as a human team would go in and explore, what they would do is they would know when to communicate with other members of the team. They would be in touch to tell other members of the team, oh, I found survivors over here. Don't go onto this floor because it's too dangerous, and so on and so on and so on. But actually what you don't want to do is swamp everybody with information. So you have to tread a path there between giving too much and giving the right amount of information. And knowing when to share information is actually rather difficult, and when and what information to share. But more than that, they also need to be able to share tasks. So what do I mean by that? Well, one can imagine as these robots are exploring, they come across a human survivor who, let's say, has a burns injury. Okay, and the robot doesn't have, a burns first aid kit with it. So what it needs is for another robot to come in with that capability. So here, what they're doing is they're sharing tasks. So I've got a problem. I've got a patient that needs treatment, somebody who's got burn injuries. So this is task sharing. And this is how typically large tasks are decomposed into smaller tasks, which are then decomposed into smaller tasks, which are spread across the team and so on. And being able to do that dynamically on the fly and understand when you need to do that and how you need to do that is a key challenge in making this dream of what's called multi-agent systems a reality. Now, for all of these things, for the ability to share information, for the ability to share tasks, we have developed protocols and techniques which will allow software agents to be able to do these things. We already have those things, and they're getting better all the time. So that's cooperation. Basically, it means software agents and robotics agents being able to work together in the same way that a human team would. What about coordination? Well, on the slide, what I've illustrated here is a scenario in a warehouse where there are two rooms in the warehouse and there are robots. And in this scenario, the robots are owned by different organizations. And this is an increasingly common scenario where you've got supermarkets, large shops, hospitals, and so on that have got robotics-based warehouses which are populated by robots from different organizations. And these robots need to be able to interact with one another safely. So in this particular scenario that I'm illustrating on the slide, there's a door, and the point is, you can guess, if ever they both try and go through this door at the same time, then there's going to be a crash. So how do they avoid that crash? It's exactly what we do when I give a lecture in my lecture theatres. At the end of the lecture, all the students run to the exits, but they manage to coordinate. They manage to all get out of the lecture theatre without crashing into one another, and that's coordination. And what coordination means is understanding how your actions relate to the actions of others and managing those interdependencies between those actions. Okay, knowing that, for example, this action will facilitate you doing something, or that this action will prevent you doing something. Coordination can be positive, I can facilitate, or it can be negative, I can prevent. So the question is, how are these robots going to be able to do this? Well, the most obvious way for them to do this is for them to model each other. So for the robot in the top left to know what the goal of the robot in the bottom right is, and for the robot in the bottom right to be able to know what the goal of the robot in the top left is. So they can model each other, understand what they're doing, predict what the other robot is going to do, and then work around that. And if they both mutually do that, then they can coordinate. So this means modeling and understanding each other's actions. Okay, next what I want to talk about is negotiation. So negotiation is a very exciting capability for software agents. Again, it's been an active research area now for 30 years or so, and we've now got a lot of experience of building intelligent agents that can negotiate. And to illustrate the scenario, I'm just using the following picture. So we've got two companies, Company A and Company B. And in this graph on the right-hand side, what the circles are locations. Think of those as houses on different streets, or as locations in a city. So the locations are numbered 1 through to 9. So there are 9 different locations. And then we've got links between these locations, and there are numbers attached to these links, and those are costs, the cost of getting from one location to another. So the cost of traveling from location 1 to location 2, for example, is 5. The cost of traveling from location 2 to location 3 is 4. the cost of traveling from location 8 to location 9 is 5, and so on. So imagine that's the amount of fuel it takes to travel from one to another, or the amount of time it takes to travel from one to the other. Okay, so that's the basic scenario. And both of our companies, Company A and Company B, start at location 1, which is the top left location on this little map. Okay, so Company A has a delivery drone that it's going to send out, so an automated vehicle or an automated helicopter, and it needs to visit 4 locations, location 5, 3, 8, and 9. So on its own, the sensible way to do that is simply figure out the shortest route that includes location 5, 3, 8, and 9, and to travel that route. Okay, and then get back to your starting place. Company B, by contrast, needs to visit location 4, 5, 3, and 9. Okay, so again, on its own, the simplest thing it can do is find the shortest path that includes 4, 5, 3, and 9, travel that path and return to its starting point. But here's where negotiation comes in. You'll notice that both companies need to visit location 3 and location 5 and location 9. So why don't they just do a bit of rearranging? Why doesn't Company A say, well, look, I'll visit location 9, so I'll take your package to location 9 if you take my package to location 3. Okay, and Company B can accept that. It's not going to be worse off. It's got one less location to visit, right? So the question is, how do they agree about the reallocation? So one solution, for example, one very quick one that I came up with is Company A visits locations 5, 3, and 8, and Company B visits locations 4 and 9. And intuitively, this kind of makes sense because location 9 is the furthest away. So Company B has to do a lot of travel to get there. Company A is visiting locations that are closer to home, but there are more of them. So you can kind of see that seems like a reasonable outcome. Okay, so this is the result. Think of this as being the result of a negotiation process. How are we going to reallocate our tasks so that they're all delivered? Well, the problem is, this is also a possible solution. Company A visits all of the necessary locations, so 3, 4, 5, 8, and 9, and Company B does nothing. Okay, so that's clearly not a very good outcome from the point of view of Company A. So what we do is we have protocols which will allow agents, software agents, to be able to negotiate with one another so that they can do that reallocation in a fair way. So I don't remotely have time to go into the details, but the basic idea is that we have communication and cooperation and negotiation protocols, which we can guarantee in a mathematical sense that neither company can be ripped off, that the outcome can only be better than they would have started out with, right? So that they can be guaranteed to be better off. And investigating those protocols and designing them so that they're efficient and fair is a big part of what we do in the multi-agent systems community. So these skills then that I've been talking about, sharing meaning, the ability to cooperate, to work together as a team, to coordinate, to manage the interdependencies between our activities, and finally, the ability to negotiate. And by negotiate, I mean negotiate in exactly the same way that we do in the human world to reach an agreement on a matter of common interest. These are the fundamental social skills that we're going to need to equip agents with, intelligent agents, if we're to realize my dream of connected AI. Okay, so let's see, this is multi-agent systems are an old idea. These are just some of the potential applications that people have been looking at. So meeting scheduling, if your life is anything like my life, then a crazy amount of time is soaked up by arranging meetings with other people, which is a kind of routine thing, but also it's quite a difficult thing because of this need to take into account preferences and so on. But automated meeting scheduling in exactly the same way that I illustrated earlier is a very obvious application of multi-agent systems. Automated commerce and micro-commerce. Automated commerce means having agents that buy and sell goods on your behalf. Micro-commerce means doing it in settings where the prices are very low. Connected vehicles. After we have driverless cars, we're going to have connected vehicles where cars out on the street are talking to one another. Agent-based workflow, agent-based simulation, these are both examples of how intelligent agents communicating with one another and cooperating and coordinating and negotiating with one another can be usefully used in the real world. So to go back to the beginning of the talk, I talked about 5 trends that have marked the history of computing: ubiquity, interconnection, delegation, human orientation, and intelligence. And just as they have marked the history of computing to date, I think they're going to be absolutely central to the future of artificial intelligence. This is what the future of computing looks like, with very, very, very high probability, which means that in AI, that must be what the future of AI will look like. So agent-to-agent dialogues, my Siri talking to your Siri, are going to be ubiquitous in the future. We just have to make it happen. I hope you found this talk interesting. I hope you found it stimulating. I hope you've got some ideas now about where we might go with agent technology. But most of all, I hope you've been convinced by my arguments. I'm very sorry I can't be with you in person for obvious reasons, but let's hope that can happen next year. Thank you very much for your attention.
Mr. Wooldridge, hello. Thank you very much for your report. It touches upon a very interesting aspect. It is absolutely to the point. So may I ask you a question?
Please do.
Okay, so you were talking about the future where AI systems do not just interact with human, but they will interact with other AI systems. So what changes in the society this might lead to?
Well, I think what we're going to move to is a future where the individuals in the society, the human beings, are just part of society, that there's going to be software agents out there that we're interacting with as well. So that, many of our interactions, the kind of things that we do in our job, that we do in leisure time, will not be with humans. They will be with software agents. And we'll just get used to that. And it may seem weird to you and me, but our kids are just going to take it for granted.
And what tasks are still too difficult for Siri to accomplish?
Well, there's a long list, and that's what makes my research area so interesting and exciting to work in. So we've made a lot of progress, for example, on building protocols for negotiation, which will allow software agents to negotiate fairly with one another. But there are still some really big unsolved problems, like the thing I talked about, sharing meaning. How can 2 agents not just use the same language, but know that when they use a particular term, that they're both referring to the same thing? That's a really, really hard problem. And we don't really understand how humans do it. We do. I mean, we're doing it successfully now, and we're thousands of miles apart. But we don't yet know how to enable software agents with that capability. So there are many unsolved problems. And I say this is what makes it such an exciting research area.
Thank you very much indeed. Thank you for joining us. Bye-bye.
Thank you.